So on Earth, if you went to a high enough mountain, and let's say there wasn't any atmosphere because that just gets in the way, and you fired off a bullet, probably at around 8 kilometers a second, eventually, if you didn't step out of the way, the bullet would come around and hit you in the back of the head. Sort of 90 minutes later or thereabouts, because the bullet would have entered an orbit. On Mars, the dust is not only abrasive, it's also chemically quite reactive. There are things called perchlorates that form on the surface of Martian soil, and they're essentially oxidants, and they're pretty aggressive. It's like, putting your oven cleaner on your skin or in your lungs. A bullet that you just drop out of your hand will fall at exactly the same rate as the bullet that you fire out of your rifle. Of course, the bullet that you fire out of your rifle will travel a greater distance horizontally, but the amount of time it will take to hit the surface will be the same. A thought experiment of trying to go to Alpha Centauri with a chemical rocket. Yeah. And it turns out if you want to do that in any reasonable amount of time, let's say 100 years, right? 100 years is commensurate with a human lifetime. You could imagine building an enormous interstellar chemical rocket. Well, it turns out that the amount of rocket fuel you would need, or propellant, is some enormous factor greater in mass than the mass of the observable universe to do that. Right? So you could build a chemical rocket and get to Alpha Centauri in 40,000 years, 50,000 years. In fact, we've pretty much done that with the Voyager probes. But anything quicker than that, and chemical rockets are not going to get you there quickly enough.
All right, everybody, it's time for another episode of the Michael Shermer Show. It's me, your host, Michael Shermer. My guest today, Caleb Scharf. He's an astrobiologist and recipient of the 2022 Carl Sagan Medal. Hey, there's Carl right there behind us. I don't know if you can see that in this shot there, but anyway. He was Director of Astrobiology at Columbia University in New York, and he's now the Senior Scientist for Astrobiology at the NASA Ames Research Center in Silicon Valley. He's the author of more than 120 scientific papers and over 500 popular science articles published by Scientific American, Nautilus, Aeon, and more. In fact, he was writing quite regularly at Scientific American when I was there every month. He's a frequent consultant and speaker for TV and live audiences, and his popular science books include Gravity's Engines, The Copernicus Complex, The Zoomable Universe, The Ascent of Information, and here's the new book just out, The Giant Leap, Why Space is the Next Frontier in the Evolution of Life. Caleb, welcome to the show. Nice to talk to you. Nice to finally meet you, actually. All those years I've been reading you. I'm a huge fan of your writings, and now I get to actually meet you.
Well, likewise. Yeah, pleasure to be here. Thank you for having me.
So what's your origin story? How did you get into space and astronomy and physics and all that stuff? Go ahead, back to no pre-lives, just this life.
Yeah, I'm pretty sure there weren't any pre-lives for me. Yeah, so I guess like lots of scientists, it goes back to sort of childhood fascinations with the world around me. And I guess, the scientific approach to decoding the nature of one's own existence was the thing that appealed the most to me. And of course, space, the cosmos, has always fascinated me, as it's fascinated so many people. And I think a deep need to explore that, and an excitement about what it means and the perspective that it gives us for what we are as individuals, what we are as a species, have been things that have driven me. I can say things like Star Trek and Star Wars as well, but I think those have limitations. I've always been excited and fascinated by the natural world around me, and so I chose to pursue that as a career.
Nice.
For better or worse.
Oh, no, for better, for sure. This book was so interesting. I just could not stop reading it, not only because you're a good writer, but also the details. Just so many things I had no idea, even though I've read quite a bit of popular works in this area. Your epigram for the book is from Konstantin Tsiolkovsky. Earth is the cradle of humanity, but one cannot live in a cradle forever. So, to what extent is your book descriptive? That is to say, this is the direction we're moving, and if we're going to do that, here's how we get there. And prescriptive, that is, you really think we should do this, and you're a fan, and here's how we're going to do it because we want to.
Yeah, it's a great question. So I think I've tried to avoid being prescriptive because if people really sort of put me up against the wall and ask me, is this a good thing for us to be doing? Should we be going into space? Should we be paying attention to that more than other things? I find myself a little bit on the fence. I think what I feel, though, and part of the descriptive side of the book was to really try to dig into what has been happening for the last half century in terms of our approaches to space exploration, the changes in technology, the motivations, what we've learned, and so on. Looking at that in detail to try to understand whether this essentially has a life of its own. I think there are so many things that we do as a species where we can always sit back and say, well, that was kind of a dumb thing to do, but we seem to be doing it anyway. Other people are crazy, right? It's never me. But and I think there are things that happen to any species that at some point, whether for better or worse, they're sort of inevitable. There's a momentum that picks up. And I find myself, when it comes to space exploration, the details in the book where I really tried to dig through, and there are many, many more details that could have been included, but try to find all these anecdotes, find all these intriguing instances of very specific exploration events, very specific scientific missions or human missions or more commercial enterprises that are illustrative in some way. They show us the complexity of this enterprise, but also the seeming unstoppable nature of it. It's had its ups and its downs, but that feels more like a natural phenomena than anything else. In the book, I talk a little bit about this. It's like, you may not like the idea of space exploration, but you may not have a choice. It's, the net human attention to this is such that, we can't really stop that momentum at this point.
Yeah, it does seem inevitable in the sense of our species evolving millions of years ago in the plains of Africa, let's say Olduvai Gorge, 1.5 to 3 million years ago with the Australopithecines. And from there, we've just continued expanding out of Africa, through Europe all the way across into Southeast Asia and Australia, and then eventually across the Siberian Straits there and into North and South America. And, I guess in Antarctica, I don't know if people actually live there or work there. But, those are some diverse climates. Our species seems to be well adapted to extreme environments. So it seems like, well, then what's the next move? Well, space. Yeah, but okay, so here's the objection to that is like, yeah, but all these places these hominids moved into had food and water and air, kind of basic range of temperatures that are survivable, even if you have to make clothes and invent a few new tools to survive. Space seems like a wholly different, qualitatively different leap.
Absolutely, and there's no question that it is. The interesting question, as you put your finger on, is space is really different than even Antarctica. Antarctica, there is still air to breathe. There is water if you have energy to turn it into the liquid that you might need. There is sunlight. You could probably grow food if you had the correct structures built and so on. But I think Antarctica is an interesting example because it's almost a bridge between, life on Earth that in many ways, not surprisingly, because we've evolved out of these conditions, has the right conditions for us. But, a place like Antarctica, a species like humans relies on its technology. Right? It relies on everything that it builds and carries along with it. It relies on our minds. It relies on our ideas and our capacity to devise solutions to problems of existence. So it's not a bad test bed, but it's a lot easier than space. Right? Space, whether it's just in orbit around the Earth or another planet like Mars, is incredibly hostile to organisms like us. And so it really is only because of our technology that we have any chance of existing in space. And the interesting thing about that is that if the future does involve humans being off-world in any sort of consistent fashion, it's entirely dependent on technology. And I think we have a tendency to feel that that's fragile, which may be completely reasonable based on our experience thus far. But maybe that has to be modified a little bit, that sense of technology being fraught and fragile. And maybe at some point it just sort of blends in with everything else that we do to a degree that we haven't yet experienced.
Here's how you put it at the beginning of your book. I really like this passage. In fact, this is arguably the most difficult and dangerous endeavor that humans have arrived at in our brief span as a species. It's right up there with tease the mammoth. Dive into this watery cave. It made me think of those guys that say, hold my beer while I jump out off this roof and try to make it to the pool. It's crazy things that guys do. Or try to create a utopian society. No aspect of it is simple. The engineering needed to just get beyond Earth's 100-kilometer skin of atmosphere is extraordinarily tricky. The current prospects for maintaining life in space or on a world like Mars for any length of time appear at first glance fantastically awful. The challenges run the gamut for how to handle our most basic physiological needs in space to the unknowns of how to create functional and equitable societies and systems of governance in alien environments where entirely new hazards and resources become fresh items to squabble over. Right? You cited that the volume that I contributed to. Now I'm escaping the title of it, so let me pull it up here. It was Charles Cockle's The Institutions of Extraterrestrial Liberty. I just wrote about different structures of society, small groups that either succeed or don't, depending on how vertical the structure is or horizontal the structure is. Super interesting topic. But before we get to whether the Martians are going to have democracy or what, we got to get there. So, I mean, the line you often hear is like, it would be easier to live at the top of Mount Everest than on Mars. Yep. So let's begin with just from the very beginning. Because you had a lot of interesting history of science I didn't know much about. Emily de Châtelet, Mary Somerville, Amélie Emmy Noether. I mean, those are three women in the history of science that are largely overlooked, or they're kind of footnoted in potted histories of science as, the translator of Newton. It's like, okay. But as you point out, they added a lot more than that. So let's just go back, because your whole idea, your evolutionary argument is that this next step depends on the evolution of thought. It's thought that's going to get us there, ideas. And so here's some of our important people that did that. So go ahead and pick it up there.
As writing the book and thinking about wanting to give a reader, the real basis of, why is space exploration difficult, apart from things like, a lack of oxygen and so on, the fundamental mechanics are enormously challenging. Why did it take 4 billion years for life on Earth to find a way to purposefully remove itself from that point of origin? And part of the explanation for that, I think, is in physics. And physics is lovely. I love physics. That's my background. And so I wanted to dig into that and point out that your biology is extremely frugal with energy in general. And the spatial concentration of energy flow that biology utilizes is tiny compared to the kind of energy that you need to actually climb out of a gravity well on a planet. And so it required something new to happen for terrestrial biology to gain the ability to get into space, I think. And that something new is thought, as you mentioned, and it's the capacity to not just build technology, but to construct models of the world that allow us to accurately predict the outcome of certain actions. What happens if I throw kerosene and oxygen into this chamber and ignite it with a nozzle at one end, right? And how much of that do I need to do to move from the surface of a planet up into space, up into orbit? How do I compute the energy required to go from stationary to in motion? How does an orbit function? How do I describe that accurately so that I can place myself in an orbit, or I can change my orbit? And, the history of that has been told many times through people like Newton and Leibniz and so on. And we point at Newton and say, what a genius. And of course he was. But his materials were also pretty difficult to get to grips with. I mean, especially since so much of it was new 400 years ago. And I got interested in, concepts. Where did the concepts of things like energy, potential energy, kinetic energy, where did those really come up as people were working this through? And it wasn't really Newton who managed, who focused on that particularly. And so there's some really interesting history about these concepts of energy, these concepts of things like momentum, which is the product of the mass of an object times its velocity of motion. And it turns out that some of the people who had interesting stories around their lives and their engagement with this were these three women that you mentioned. They were separated in time. Emily du Châtelet came right after Newton and didn't really overlap with Mary Somerville or Emmy Noether, but they each sort of added a piece to this scaffolding of thought, which articulated, mathematically and even philosophically these ideas of energy and change in the universe. How does change take place? Why are some things conserved in the universe? Why is the total energy of something always conserved? Energy can transform into different forms, but the total amount of energy appears to be conserved in systems like rockets or anything. And, they're three fascinating people. Emily du Châtelet, was Voltaire's lover. I mean, who knew? I didn't know that. And here's this woman engaged in the thick of interpreting Newton's physics and kind of progressing it forward. And I think we don't always give enough credit to people who, they may not write down a fabulous equation that changes the world, but they figure out how to interpret an equation. They understand that it's a dialogue between people to progress knowledge to the next level. And then people like Mary Somerville, who is an extremely adept mathematician, taking the works of others and synthesizing those and making them digestible is an incredibly important thing to do. And of course, she was more than that. She understood this and was able to add nuance to the mathematics, which described things like orbits and energy in more detail. And then you had people like Emmy Noether in the sort of early 20th century, who was an astonishing mathematician, who saw a way to a fundamental proof that symmetries in space and symmetries in time are actually the things that give rise to these conservation laws. And all of those things you have to understand if you're going to build a rocket, if you're going to design an orbit, if you're going to move through our solar system. You need all of that. So I thought it was an interesting thing to dig into that I had not fully understood. And I think, and I mentioned this in the book, you can always pick people to tell your story through. So I could pick other people. I could pick Newton and the usual suspects in this. Mm-hmm. But I wanted to just step back for a little bit and remind us that, these ideas, these moments of scientific progress, they're a web of people and they're a web of thinking. And it's quite fascinating when you look at that. And it also makes it feel more integrated with the whole trajectory of our species, to understand that it's not just a few individuals. And it's not just the people who write the first equation down. It's the people who interpret those equations down the line that are equally important.
Cumulative knowledge. in the sense that I always like David Deutsch's book, The Beginning of Infinity, where you're, constantly trying to solve problems and find good explanations or solutions to problems, and then once that's done, you can keep building from there because that's just going to uncover new problems to solve and explanations to search for and so on. And that's really what you're tracking there. Now, let's go through a couple of ideas that fascinated me. Energy. You always think, well, I know what energy is, and you make that the joke about the science fiction creature. Oh, it's a pure energy creature, like it's a thing, like it's a ghost hovering there, or whatever. It's so crazy. But so like I'm holding this pin here, and it has no energy, right? But I'm dropping it, so it has some potential energy or whatever. See, you physicists have these different terms. What do you mean by energy?
Yeah, so energy, it's a tricky concept because it's not a thing, right? Which is why I made the comment about the science fiction stories where you've got a being of pure energy, and I always wince when I hear that. It's like, what does that mean? Energy is in something. Energy is about changes that take place in the world. It's a descriptor of the extent to which change can take place in the world. It's a descriptor of the capacity for things to perform actions or to change. So when you hold your pen up, a physicist would say, well, you've raised the pen up, and so it has a certain amount of gravitational potential energy. That is energy that is there because it's sitting in a gravity well. And what it really wants to do is slide or fall through that gravity well, but you're preventing it. And so the energy is not yet instantiated. It's potential. The moment you let go, that potential energy transforms into an energy of motion that we call kinetic energy. And of course, when the pen hits your desk, right, it makes a sound, it stops. That energy of motion is now transferred into sound waves. It's transferred into thermal energy as the pen hits the desk. I mean, you can't, human sensors aren't good enough to sense that, but you could, in principle, measure temperature changes because you've dropped it, a couple of feet onto your desk. But of course, all of these things are incredibly abstract. They're very strange concepts.
Even my lifting it takes some energy, and that you can account for by the food I ate because that fuels the muscles.
Yeah. No, it's that action is actually really complex. The flows of energy necessary for you to do that are complex and intricate and play out over a number of different timescales. So, yeah, in the book, I wanted to I spend a little bit of time just dissecting this notion of energy because it's so important. It's part of the vernacular, but we tend not to really understand what it means. And it really is about about change in the world. And so the beautiful thing about dropping your pen on the desk is there's a continuous transferal of potential energy into kinetic energy. Yet the total amount of energy in the room remains the same throughout that entire process until the sound waves, echo out of the window in your office or whatever. And that's really important for space exploration because that exchange or interchange between kinetic and potential energy is part of the way that we produce mathematical descriptions of things like orbits. It's part of how we compute what is necessary to propel a rocket into space and into an orbit, what's necessary to get us onto Mars and so on. So it's really fundamental, but it's, it comes out of these very abstract thoughts that we have about the nature of the world and how things happen in the world.
Yeah. So the problem to solve is how can I get my capsule into orbit around the Earth? Well, you got to calculate how much energy you need based on how much mass you're going to try to put up there and so on. So you kind of go through all those calculations. Can you remind me, I remember when I had Astronomy 101, the professor used the analogy of, if I had a rifle parallel to the ground I'm standing on, and at the moment I shoot it and I drop a bullet just straight down, they hit at the same time. Is that true? And that always struck me as really counterintuitive.
It is true. right? And so what's going, and this is a beautiful way to begin to understand what we mean by orbits, which I suspect is why you've asked me that.
Yes, exactly.
Yeah, so the gravitational acceleration on the Earth is always acting towards the center of the Earth, right, in a radial direction. So every time you drop something, it's always falling. If you don't give it any lateral motion, it falls in a straight line directed towards the gravitational center of mass of the Earth. And it doesn't matter what the lateral motion is, that force, that radial force, which is often just perpendicular to the lateral motion, is always going to act in the same way. And that acceleration is always going to be the same. So the bullet that you just drop out of your hand will fall at exactly the same rate as the bullet that you fire out of your rifle. Of course, the bullet that you fire out of your rifle will travel a greater distance horizontally, but the amount of time it will take to hit the surface will be the same. However, we live on a sphere. And so the surface that it's flying above, the bullet that you fire, is not flat, it's curved. And that curvature is well, what that means is if you fire your bullet fast enough, it will fall at exactly the same rate as the planet is curving away from it, as the surface is curving away from it. And so, Newton had this lovely illustration, and he used this as an example to think about what an orbit is. He had a cannon, or we assume it was a cannon on a mountaintop. Yeah, that's exactly it. That's the original illustration. And so he imagined this mountaintop. We'll assume it was a cannon. It fires a cannonball at different velocities. So if it's a modest velocity, the cannonball flies out. It may go some distance, but of course its trajectory curves down until it hits the surface of the Earth. If you fire it fast enough, it will continue to fall towards the surface of the Earth, but in every moment of time that it progresses, it's also moving ahead fast enough that it actually follows the curve of the surface, and it never actually intersects the surface. And that velocity puts it in an orbit. And so it's an interesting way to think about what an orbit is and to relate it to being on the surface of a planet. So on Earth, if you went to a high enough mountain, and let's say there wasn't any atmosphere because that just gets in the way, and you fired off a bullet, probably at around 8 kilometers a second, eventually, if you didn't step out of the way, the bullet would come around and hit you in the back of the head. Sort of 90 minutes later or thereabouts, because the bullet would have entered an orbit. On Earth, things are complicated because of an atmosphere and friction, and we're not used to things moving that quickly. Because things moving that quickly tend to basically fall apart because of atmospheric friction. And so this is one of the challenges of rocketry, is to achieve the kind of velocity where you're still falling, but you fall at the same rate as the Earth is curving away from you. Means you need to get out of the atmosphere, and you also need a pretty enormous amount of acceleration to get you up to those kinds of speeds.
Yeah. I always like that footage from the Apollo astronauts dropping the geology hammer and the feather at the same time, and they land at the same time. And I used to do a demonstration in one of my history of science classes of the heavy ball and the light ball. And it's actually hard to do because you're holding the heavier ball stronger with your fingers, so it takes a moment longer to let it go. So it's hard to get them to hit at the same time. Anyway, but that's the idea there. So that would be what is that, 17,500 miles an hour for a rocket to get into orbit?
That sounds about right. I
like
think
that,
in terms of kilometers per second,
right.
because I'm a nerdy physicist. So
That's right. Yeah. And then escape velocity is 11.2 kilometers per second, or 40,270 kilometers per hour to escape the planet's surface. By the way, I discovered something recently, because I had this weird thing in my head about the Apollo spacecraft, when they launched it when they actually did the last stage toward the moon, They got it up to 25,000 miles an hour. I guess you're 40,000 kilometers an hour. So 25,000 miles an hour. The moon is 250,000 miles away. Why doesn't it get there in 10 hours? Why does it take 3 days? And then it was explained to me because the Earth is pulling it back all the way, slowing it down, slowing it down.
Right. Yeah.
So you have to calculate all those things. And then at some point, I guess the moon is pulling it a little bit to counter the Earth's pull.
Yeah, no. So yeah, calculating any kind of trajectory in space, outside of off the surface of an object is really difficult because you have to take into account not just the gravitational pull. So as you say, climbing away from the Earth, there's those Apollo astronauts, they basically coasted towards the moon. And as they coasted, initially they were slowing down because the Earth was dominating the pull on them. But then as they got closer to the moon began to pull them more towards it. And so it's an interesting dance that takes place. But the complication is everything is moving. The Earth is moving around the sun, the moon is moving around the Earth. And so to make sure you end up where you want to be, it's not super complicated, but it's difficult mathematics, and it's mathematics that you have to be really careful about. You have to take into account everything that's going on, the fact that everything is in motion, and these, the energies, the velocities, and so on.
And so is that not a three-body problem that we often hear about as so difficult? You have the Earth, the moon, and the spaceship.
I mean, it is essentially a three-body problem. Yeah, and the famous quote of Newton, who basically, he was able to perform calculations of one object orbiting another object because of gravity. When he tried to perform calculations of three objects in mutual gravitational pull and their orbits around each other, it suddenly becomes incredibly difficult, and the mathematics sort of explodes in complexity and difficulty. And he kind of had this comment about, it seems, beyond the means of any human to to do this. I mean, we now can make those calculations using computers, using digital computation. We can in fact make calculations of systems with almost an arbitrary number of objects that are pulling on each other gravitationally, but it is very challenging. And you do run into situations where systems become chaotic, and a three-body problem can easily become chaotic. Now, for the astronauts and the Earth and the Moon, the situation's a little bit better because it's a sort of restricted or constrained problem. The Earth and the Moon have somewhat different masses, and of course the spaceship has tiny mass, so it's like a little test mass that is flying between these objects, and it's all happening in a restricted plane of motion by and large, and so that helps. But yeah, you have to be really careful when you're computing spacecraft trajectories because of all of the subtle effects, especially over long distances and longer times, that can accumulate and make systems less and less predictable.
Another one of your heroes of your book is Konstantin Tsiolkovsky, who I continue to be more and more impressed by the more I learn about him. You talk about his rocket equation as the mass ratio of the initial total rocket mass to the final payload grows. So does the final rocket velocity, but that velocity grows less and less easily with the larger mass ratios. Here's your curve describing the equation. This seems to be a limitation of chemical rocketry. I mean, the title of his 1912 paper is The Exploration of Cosmic Space by Means of Reaction Devices. So the energy they're using there is a reaction. It's a Newtonian, reaction motion, and that's just chemical rocketry, and that has this limitation that Tsiolkovsky is. Talk about that a little bit more.
Yeah, gosh, it gets technical really quickly. And even Tsiolkovsky's equation, it incorporates a natural logarithm and so on. And for most of us, that we glaze over pretty quickly. But as you said, what it tells us is maybe the easiest way to think about it is just the sort of thought experiment. Okay, I want to accelerate, and I want to be able to accelerate hard and fast as much as possible. But in order to do that, I need to throw as much stuff out of the back of my spacecraft as I can. And that's what a rocket is. Rocket is essentially just throwing mass out behind you. And we know from Newton, for every action, there's an equal and opposite reaction. So by throwing mass out in that direction, I inevitably move in the other direction if I'm out in space. And so that's the basis of rocketry. So I want to throw as much mass out the back as quickly as possible. But that means I have to carry that mass with me in my rocket fuel and my fuel and my oxidizer and so on. And it turns out that, and this is what Tsiolkovsky showed with his relatively simple equation, although it's a little hard to intuit, is that it's almost like a Zeno's paradox, right? You want to go faster, so you've got to take more stuff along. But that means until you've thrown that stuff out of the back, you've got to accelerate it as well as your own mass. So you might have a beautiful, sleek spacecraft, but it has to be attached to this enormous tank of propellant that you have to carry with you until you can get rid of it all. And that means that you're having to push all of those propellants until they can be utilized and squirted out of the back of the rocket. And this is really bad news for chemical propulsion, because it turns out that there becomes a point, you showed my little picture with the curve, that basically is diminishing returns. You can make your rocket bigger and bigger and bigger, and you can have more and more fuel, more and more propellants to push out, but depending on the properties of those propellants, how quickly they can be squirted out the back of the rocket, you essentially plateau in terms of the final velocity that you can possibly reach with a chemical rocket. And because chemical rockets rely on converting chemical energy into kinetic energy by essentially burning ingredients or having ingredients react to raise their temperature, there's a limit to the combinations of substances that you can put together to produce a good rocket exhaust. And we don't know of any chemical combination that gets you beyond a certain point. So in the book, I use this example, a thought experiment of trying to go to Alpha Centauri with a chemical rocket. Yeah. And it turns out if you want to do that in any reasonable amount of time, let's say 100 years, right? 100 years is commensurate with a human lifetime. You could imagine building an enormous interstellar chemical rocket. Well, it turns out that the amount of rocket fuel you would need, or propellant, is some enormous factor greater in mass than the mass of the observable universe to do that. Right? So you could build a chemical rocket and get to Alpha Centauri in 40,000 years, 50,000 years. In fact, we've pretty much done that with the Voyager probes. But anything quicker than that, and chemical rockets are not going to get you there quickly enough.
Yeah.
Which is shocking.
Even 100 years is a long time to sit there with your seat back and your tray table down. Right.
I think you'll use up all your Netflix subscription.
Yeah. I mean, just I always use this example of just how vacuous space is. The Voyager spacecraft, fastest thing we've ever built, I guess, or at the time it was. If it was heading to Proxima Centauri, it would take, I don't know, like 70,000 years to get there or something like that. And that's the closest star. It's mostly just empty space. And it's just yeah. This is my answer, by the way, to the Fermi paradox. Where is everybody? They're probably out there somewhere, but it's just mostly empty space. The chances of them getting here are pretty much nil. Okay, so Hermann Oberth, another one of your heroes, the Oberth effect is related to what you just described?
Yeah, so there are these interesting phenomena that not often talked about in terms of rocketry and astrodynamics, getting around in space. And Oberth I guess he was in the early 20th century, came up with this realization that when you're moving and you add energy to your motion, it's more efficient than when you're stationary, which is very strange. So what it means is that if you want to, for example, go to a planet like Jupiter and slow yourself down at Jupiter, you might do it by trying to orbit around the back of the planet and using some of the gravitational pull of the planet and so on. But it turns out to really affect your motion the most, you actually want to apply, in that case, the brakes when you're moving the fastest, which is counterintuitive. And it's basically what he showed is you get more bang for the buck in terms of your expenditure of energy, in terms of changing your kinetic energy, the faster you move. So the faster you move, the more effective your rockets become, which is good news in many respects. It's also surprisingly counterintuitive. And I've encountered people of some stature, physicists of some stature, who perhaps even hadn't heard of the Oberth effect because they've not engaged with rocketry or propulsion. And when you talk to them about it, and it's relatively simple to see when you write it out mathematically, but they still disbelieve it. It's like, that doesn't make any sense. The faster you're moving, the easier it is to utilize the energy for propulsion. But it comes out of the mathematical structure of kinetic energy, which is the mass times the velocity squared. And so you can change your energy very effectively with a little tiny change in velocity, because you're squaring that velocity to get the kinetic energy. The kinetic energy and its relationship to potential energy is what determines your orbit and so on. So there are these interesting facets of rocketry and space exploration I think most of us are oblivious to, except for the people who actually
and most of us also forget it. No matter how fast you get up to get to where you want to go, you have to slow down unless you want to just blow by and just take a few pictures and keep going.
Yeah, no, absolutely. And this, of course, has dictated a lot of the ways we've explored our solar system. I mean, the first efforts to get to places like Mars involved flybys. And that wasn't because people didn't want to stop. It was because it would have required so much extra fuel and machinery to actually slow you down enough to be captured into orbit around Mars. So it took us a while to do that. It took quite a few years and multiple attempts to be able to actually slow down, get captured into orbit around Mars, around Venus, around other worlds. Yeah, slowing down is just as much of a problem as speeding up.
Okay, this cluster of characters, Konstantin Tsiolkovsky, Robert Goddard, Werner von Braun, Jack Parsons, Hermann Oberth. It's kind of this cluster of characters, before the space age of the 1960s that, all came online around the same time. It's an interesting sociology of science and technology. I think if Emily de Châtelet was a colorful character, Jack Parsons makes her look tame. What a character he was.
I don't even know where to begin with that. But so he was kicking around in the 1940s and 50s and 60s and was part of the origin of the jet propulsion laboratory in Pasadena in California. Parsons, I'll probably forget some of the details of his story, but they're all in the book. He came out of a fairly strange family that had wealth and then lost it, and clearly had all sorts of sort of internal issues as a family. And he was both a very brilliant rocket engineer, and rocketry was still relatively new at the time, and he worked with a group of people to do things like the first sort of rocket-propelled aircraft for the United States and the beginnings of solid fuel rocketry for the space program. But he was also into the occult, and he was also into having plenty of drugs and affairs with people too closely related to him and all sorts of things.
And he left his wife for her 17-year-old sister, did cocaine and methamphetamine. He belonged to the order, the order of the Templi Orientis, Scientology. Yeah, it's you wonder by temperament and personality if maybe those oddities also made him so open-minded. He could also see things in science that other people weren't seeing.
I think that's a really great observation, and that is my sense of it as well, that people like that, especially at that time and that sort of moment of sort of technological progression, especially for things like rocketry. Rocketry is so outrageous. Even today, it's pretty outrageous. But imagine, in the 1940s, 50s, and 60s, and so on, as it was undergoing this rapid evolution, you had to have people willing to take crazy risks. You had to have people willing to really think out of the box. And so someone like Jack Parsons, it was perhaps not so surprising that he and others like him played a big role in this. They were willing to try things and to, imagine an outrageous future that, more conservative people might not have imagined. Of course, his story was particularly tragic. In the end, he basically blew himself up in his home laboratory. But this is after he was forbidden from working anymore in rocketry because of his various other extracurricular activities. He just the military and the security services in the US just no longer trusted him. But yeah, colorful characters like that, and even people like Wernher von Braun, certainly a colorful character, whatever else he was. There are these moments in history where just the right kind of mix of crazy and smart seems to do things.
The Parsons story is the version of "Hold my beer while I try out this new rocket I just created." Remember the Darwin Awards? Given out to people who take themselves out of the gene pool before they reproduce. Yeah.
I mean, in retrospect, it's amazing he lasted as long as he did.
But in terms of like a counterfactual, but for World War II, then Wernher von Braun probably wouldn't have had the resources to develop rocketry at the pace that he did, because Hitler wanted these wonder weapons when things weren't going so well. So he ended up in Peenemünde, which was a pretty questionable place for slave labor and all that stuff that he kind of memory hold for everybody, as did the U.S. government. Because I don't know how much you know about Operation Paperclip, but Annie Jacobson's book on this is just stunning. How hypocritical it was, but on the other hand, the Russians were doing it too. That is to say, let's get as many of these German scientists and chemists, physicists, and so on our side before the Russians get them. And so they put a paperclip on the folders of the ones that they wanted. The rest went off to Nuremberg to be held trial for war crimes. And these guys were given, like homes and jobs. Yeah. It's a crazy story, but for that, probably it's hard to say, what the pace would have been for rocketry development if we could have gotten to Apollo by 1969.
No, I think, one can feel very strange about that particular history and also ask, what would have happened were it not for that? And I think my feeling is that all of this was inevitable. It would have taken longer, almost certainly. But the beginnings of it were already there. I mean, you had people like Robert Goddard in the US in the early 20th century, long before World War II, building the first working liquid rockets. I mean, they were very small, rudimentary things, but the motion, things were in motion already. And I think it would have happened. But yes, it was undoubtedly accelerated by things that were pretty atrocious in all reasonable
in terms
ways.
of, I agree. It probably would have happened. I liked Matt Ridley's book, How Innovation Works. I think that was the title. Sorry, Matt. How nothing comes out of a vacuum. All inventions and innovations have predecessors to them, and they're cumulative. So there's a sense in the air for the time. One example is the light bulb, the telephone. The search engines, the Google guys got it, but there were already search engines. Somebody would have figured out the page ranking system, that kind of thing. If not that year, within a few years. Same thing with Bill Gates, and he came online just when hardware needed software and he had the right program. But it's not like, no one would have figured that out for another century. This would have happened soon, right? So probably the rocketry, we would have gotten to the moon, in the 20th century, very likely.
Yeah, I agree. I mean, it would be interesting if only one could play out that alternate timeline. It'd be interesting to know whether, for example, suppose the impetus to take people to the moon had come out of a different scenario, right? A more methodical, thoughtful scenario rather than the rather jingoistic
space race,
impetus that certainly in the US, but also in the Soviet Union, right? I mean, became a matter of national pride and so on. You kind of wonder whether, an alternate Apollo or Soviet space program that was not motivated in the same way might have taken longer, but then it might have persisted. It might not have folded rapidly afterwards. I mean, there's these efforts where you throw money at something just to, accomplish something without a real plan afterwards. They tend to, stall things in the longer term. You may make these breakthroughs, and there's no doubt that certainly the Apollo missions were extraordinary technological breakthroughs and accelerated things in many ways. But then,
well,
their
von
political
Braun had
nature.
all those plans to get us. Yeah. Then Braun had all those plans to get us to Mars before the end of the 20th century. So I guess that shows just how political also it is. Somebody has to fund these projects and be motivated to do so.
Yep, absolutely. I mean, I think what's so interesting right now is this changing landscape of space exploration with the real rise of independent commercial space interests in a way that hasn't really happened before. I mean, we've always had the aerospace industry engaged, certainly in the Western world, with space and big companies like Boeing and Lockheed and so on making their contributions. But now with the rise of private space launch systems, but also spacecraft construction systems and peripheral technology. I mean, I was astonished to learn recently, actually, after I finished the book, that globally there is something like 10,000 space companies, whether startups or established, which is amazing, right? And that, I think, is an indication that there's a shift here. And obviously a lot of it is driven by economics, but it's also, there's generations of people who retain their excitement about the opportunities of space, of the good that can come out of access to space and the open-ended nature of space. What does it, maybe there are some fantastical things that can happen for us as a species. And I think that's contributing to this shift to some extent from state-funded to, privately funded space efforts.
Now we move out to the moon. So here's another one of these tidbits from your book that I just had no idea. You're talking about the Earth's magnetosphere, an invisible region of space around the Earth spread across tens to hundreds of thousands of kilometers in a distorted teardrop shape. Teardrop in terms of the motion that the Earth is moving, so the bow is out here and the teardrop's behind, something like that.
Well, kind of pointed away from the sun because it's the solar wind is
like
pushing.
A comet then.
Yeah, exactly.
So it's delineated by the ephemeral sheet-like structures of moving ions and electrons where the planet's magnetic field supports life against the flowing electrons and ions of the solar wind. It's a little like the keel of a ship placed in a fast-moving river. Now, here's the wild part. This is just crazy. During about 4 days each month, the moon passes through the tail of this invisible structure, and atoms that are stripped from the Earth's outer atmosphere can stream through the magnetosphere sheets to land directly on the lunar near side. Japan's Kaguya lunar orbiter, however you say that, which operated from 2007 to 2009, encountered these sheets of particles many times. It appears that oxygen atoms that form an Earth's ozone layer and then diffuse upwards to space are being carried to the moon, where they end up implanted in the lunar soil. That's just nuts. I had no idea.
It is. Yeah. I had some vague knowledge of this, and then I looked into it for the book. Yeah, no, it is. And what is so remarkable is this must have been happening for a long time.
Yeah, billions a year, or
And
hundreds of millions.
and I
Anyway.
touch on that in the book, and this, that these oxygen atoms and other materials from the Earth's atmosphere have been implanted on the lunar surface, well, for as long as we've had a magnetic field, and as long as there've been atoms of oxygen in our atmosphere. So, what's fascinating about that is twofold. First of all, there's potentially a historical record of Earth's atmospheric composition actually painted on the near side of the moon. If you could drill and dig and decode those implanted materials. But then there's also the possibility that some of the water that we think exists in frozen form in the deeply shadowed polar regions of the moon, some of that water ice may be a consequence of the oxygenation of the Earth's atmosphere by organisms over the last several billion years, because those oxygen atoms combine with hydrogen make water molecules. Mm-hmm. And so, it is this very intriguing and strange situation that if that water ice becomes useful for us as we explore the moon, and it is a target of exploration because water ice is a fabulous resource. You can split it with electricity to make hydrogen for fuel, oxygen for breathing, and of course humans need water for drinking. And so those lunar ice resources are a target for future lunar exploration. It's one of the areas that certainly the US is focused on, and the southern polar region of the moon and so on. But wouldn't it be strange and extraordinary if that water ice was there because 2.5 billion years ago, life on Earth started producing oxygen? And then, it's like the squirrels storing the nuts for the winter. Life unlocks a resource for itself on the moon billions of years later. I mean, crazy, crazy stuff.
Okay, let's look at leaving Earth and going to the moon and Mars. But before we do that, another one of these startling stats. There are more than 45,000 identifiable human-made objects now orbiting the Earth, and as many as 140 million tiny pieces of artificial junk, like pieces of paint or like a little bolt or nut one of the astronauts dropped or something. This reminds me of the movie Gravity. I assume you probably saw Gravity. Is there some truth to that? I mean, you could get this cascading effect. Oh, you talked about that in the book. What's that called? There's an effect named after somebody. The Kessler effect. Right.
Yes.
So once you get impacts started, then it creates more impacts, and it's almost like a fission effect.
Yeah, no, exactly. So it is a possibility, especially in low Earth orbit, where stuff is more closely packed than it is in higher orbits. Things like geocentric orbits, geostationary orbits are much, much further away, and so objects and materials are more sparsely distributed. But in low Earth orbit, there is the potential that the density of stuff reaches a critical level where if there's a collision and that collision spews out a bunch of particles or chunks of material, and those chunks also then hit other chunks, exactly like fission, you get this cascading effect, and it's an exponential effect, and so everything ends up hitting everything else. And those collisions can not only alter the orbits of satellites, or damage satellites, it could result in material just raining back down into the Earth's atmosphere and burning up. In which case you sort of, on the one hand, you sort of clean things out, but you've also made near-Earth space essentially for a while useless for doing anything, useless for all those Starlink satellites or low Earth observatories, or even the space station is in a hazardous zone. It's about 400 kilometers up. So the movie Gravity, while obviously it took some liberties, there's some basis for worrying about when do we reach a point where we've put so much stuff up there that all it will take is one unfortunate collision, and then you get this cascading effect where everything just gets smashed to pieces in orbit.
So the problem
it's a
is the
concern.
speed, right? Even if it's a tiny speck of paint, if it's moving 40,000 kilometers an hour and hits something, it's going to be
That's right.
catastrophic. Yeah.
Yeah. Yeah, it's those relative velocities are the things that get you.
Yeah. All right. So, but is there any problem of of a rocket, with a capsule going to the moon or Mars, going through that area? Is it still pretty vacuous out there, and
It's
they have to
still,
worry about?
yeah, it's still pretty sparse by normal human standards. The odds go up, obviously, but a rocket sort of exiting Earth's sort of lower orbital zone, it's going to be moving pretty fast. It's not going to spend much time in the area of danger.
Yeah.
So, yeah, it's a low probability, but you always have to be concerned with that. I mean, this is one of the aspects of space exploration is you have to have redundancies and plan for every possible
Yeah.
contingency.
Okay, so we're past that, and then the next thing we face is radiation. So one of the arguments the no moonies make, as I call them, that we never went to the moon, is you can't get past the Van Allen belt because the radiation will fry you. Well, but there's some truth to that, right? I mean, there's some radiation we should be concerned about and shield for it. And
Yeah. So, I mean, the Van Allen radiation belts are these zones where particles like electrons and protons do get sort of temporarily trapped because of the structure of the Earth's magnetic field. And so there are certain altitudes of orbits where you find yourself in those zones, and that's not a great thing to be in. But it's not a showstopper. You can either choose to orbit beneath them or above them or in between some of these belts. They're not gonna be awful to pass through. Where the problem becomes more acute is when the sun is in an active mode, so solar flares and coronal mass ejections, which are these enormous outbursts of material from the sun. Those are things of concern, and even today, on the space station, if there's evidence of a solar ejection coming towards the Earth, the astronauts do have places on the space station that are better shielded than others, and so they will seek shelter there until the storm has passed. This particle radiation, electrons, protons, and so on, you don't want to be exposed to that for too long. And this is one of the challenges as you go further from the Earth, though, is actually you get outside of the Earth's magnetosphere and its protective sort of sheath. And so the lunar surface, absolutely, you have to be very, very aware of what's going on, particularly with the sun. There's also radiation that comes in from the rest of the universe, so-called cosmic radiation. That tends to be much higher energy particles, so they're moving more rapidly. And sometimes that's good, because they'll just zip right through you and they won't do anything. It's when stuff stops and when that kinetic energy gets dumped into you is when it's problematic. So yeah, exposure on the moon is a concern. We were lucky with Apollo. There were solar storms going on during the period of time that the Apollo missions took place. And, if the timing had been slightly different, at least one or two of those surface missions would have been in trouble. A solar storm on the surface of the moon is not pleasant. And this problem continues when you go further out into the solar system, and certainly for Mars, which doesn't have a strong global magnetic field, and it has a very thin atmosphere. And so radiation on Mars is pretty bad. You have to be very aware of it. You probably need to, the first thing you do when you get to Mars is probably dig an underground bunker.
so, how much shield do you need? And do you need lead, or how about would water do it?
So it depends, yeah. So, something that's interesting about shielding yourself from radiation is it's complicated. What you're trying to do is block or slow down particle radiation in particular. And so water's not bad. Things that contain a lot of light elements can actually be quite useful, because what you want to have happen is if a particle of radiation comes in, much like a game of billiards, what you want is it to sort of bounce off of something where it exchanges some energy in a relatively gentle way. What you don't want is like that particle to hit the cluster of billiard balls and they all suddenly scatter in all directions, because if that's happening inside of you, that's not going to be pleasant. So some of the materials that work well for radiation shielding are actually lighter elements. So lithium or hydrogen-rich materials like plastics can actually be quite good. Lead is okay if you've got a lot of it, but it's heavy.
Yeah,
right? And that
you got to
mass
get it up there.
yeah, so that's tricky for your spacecraft. On Mars, the most obvious thing is to put Martian soil above you, is to quickly stick a habitat underground. But there too, you have to be cautious. So you might think, well, a few meters of that will protect me, and that's true for the radiation that comes from the sun. But higher energy cosmic radiation will zip through a few meters of that regolith pretty readily, and then what happens is secondary radiation. So that high energy cosmic radiation may then hit something in your shielding, and that will spray out new particles, which may be very damaging to you. So the bottom line is, radiation is an absolute pain in the ass to deal with, and it's something that we have to really get to grips with in a way that we haven't before. I mean, I think the current interests in returning people to the moon will help us tackle some of those problems in a way that we didn't have to for Apollo because of the length of the Apollo visits. Longer stays on the moon are going to require a lot more work and thought put into radiation shielding, and obviously Mars too. But yeah, radiation is one of the worst things that you encounter beyond the surface of the Earth.
So they can't just take a case of sunblock level 100.
That would be nice. I mean, you probably do need that on Mars because the ultraviolet radiation is also really potent on Mars because there's no ozone
By the way,
layer.
these cosmic rays, when you say they're coming from the universe, I mean, do you mean from like distant quasars that are like a billion light years away or something?
So that's one potential source. So supernova explosions can generate high energy particles. So when I say high energy, I mean fast moving. So these particles are moving very close to the speed of light. So they're zipping through the universe, and they carry a lot of energy. Black holes accreting matter like quasars, or even more subdued versions of that, are also thought to be potential sources for many of the cosmic rays that zip through our solar system. And the precise mechanisms of the generation of those particles is still a topic of study. But the environment around black holes, environments in shock waves from supernova explosions, all seem to be places where you can generate these high energy cosmic rays that are just streaming through the galaxy all the time.
All right, let's talk about what happens to your body when you go into space. By the way, I'm not leaving Santa Barbara. I'm staying right here. I'm not going anywhere. After reading this stuff, forget it. I mean, these astronauts have to take all these. I had no idea all the meds they have to take. The bone density loss, muscle loss, but stuff in their eyeballs, all this crazy stuff in your blood and stuff you were talking about. The record here: 437 days aboard the Mir space station. Valery Polyakov. But if you're talking about living on Mars or being gone for, years, and there's people that say they would go and never come back. Well, okay. How are you going to deal with all these problems? So talk about biological problems.
Yeah. So, we're a product of the Earth. And so our bodies evolved in an environment with a certain amount of gravitational acceleration, a certain radiation environment, obviously an atmosphere and so on. And, so the experience of astronauts in orbit around the Earth, where they're in what's called microgravity, so they're essentially falling, like we talked earlier about, an orbit is essentially a perpetual falling. So they feel weightless. Human bodies respond very rapidly to that condition. The way fluids are distributed in our bodies changes pretty quickly. That will adjust over time. But yeah, the deposition of material in our bones changes very rapidly. Our cardiac condition changes very rapidly. On top of that, there's radiation impacting things in our neurological system and our immune system. Mars has many of the same issues. So Mars, the surface gravity of Mars is a third that of the Earth. Now, the interesting thing is we don't really know what that does to us long term. We know what microgravity does pretty well, at least for periods of, months to a year or so. To me, this is, there are many unanswered questions about the physiological, biological impacts of being on a place like Mars. So the gravity is going to be an issue. There are drugs you can take, right? You can take osteoporosis type drugs to help mitigate bone loss. But you need to probably take things to keep your kidneys working well, because there are going to be more minerals passing through your kidneys.
Yeah, kidney stones. Oh my God.
Kidney stones.
In space. That can't
apparently, your microbiome doesn't particularly enjoy being placed into, space conditions, whether it's the reduced gravity or whether there's something about the radiation environment or just a stress response. We don't fully know. People are studying the way the microbiome changes in space, but astronaut stomach is an issue, and having an upset stomach is probably not the best thing either in 0G or on the surface of Mars. But then there are potentially neurological things that happen because of all the other physiological things going on to our bodies. There's some evidence based on experiments with rodents that radiation conditions, even if they're mild, can have an impact on our neurons. So I know at some point I've had a conversation with people. I said, "Oh, so you get to Mars after 6 months, sat out there in interplanetary space, exposed to radiation and so on, and you're stupid because your neurological condition has deteriorated. This is perfect, right? Just what you need is to put humans on the planet who can't function anymore." So yeah, there are a lot of things you need to deal with. And then on a place like Mars, and we saw this to a limited extent on the moon, the environmental chemistry, even if you're in a spacesuit, you're inevitably going to get dust and dirt and stuff from the outside coming into your habitat or on your person. You may end up breathing it. This happened to the Apollo astronauts. They were getting lunar dust everywhere, and it's extremely abrasive. On Mars, the dust is not only abrasive, it's also chemically quite reactive. There are things called perchlorates that form on the surface of Martian soil, and they're essentially oxidants, and they're pretty aggressive. It's like, putting your oven cleaner on your skin or in your lungs. And so there are going to have to be all sorts of things done to mitigate these problems. They're going to be pharmacological in nature, but they may also be, pretty demanding regimes of exercise and personal health and so on.
What about the idea of geoengineering the Martian environment, essentially creating a greenhouse effect to warm it up, and then you get bubbling creeks and squirrels running around, and you have another Earth on Mars? How realistic is that, even if it's a time frame of thousands of years?
Yeah, I'm very skeptical.
Yeah.
And my skepticism, we can definitely, come up with ideas for how to thicken the Martian atmosphere. We could say, well, we could try to release all of the frozen CO2 that we know exists at the polar caps and some of the water, although that isn't really enough to thicken the atmosphere substantially. It would make a difference. We could bring in comets from elsewhere in the solar system, volatile rich comets, and dump those down on the polar regions and so on and so on and so on. And we could dig enormous holes in the surface that allow the inner heat of the planet to radiate upwards and modify the environment and so on. My take on it is that even if you could do something as drastic as that, let's say you could thicken the atmosphere and raise the temperature on the surface of Mars, have liquid water, have your squirrels and trees for a moment. The problem is both unforeseen consequences. If we know anything, we know that a planetary climate is an extremely complex system, and we're still coming to grips with how the Earth's climate system functions. So to imagine that we could predict what will happen to Mars if we thicken the atmosphere, I think is right. That's pretty arrogant. And a place like Mars is also not particularly geophysically active, and geophysical activity on the Earth is critical for maintaining a stable climate system over not just a few years, but over centuries, over thousands of years, over hundreds of thousands of years. The feedback loops between the geophysics of the planet and its atmosphere, we've now learned are really critical. And so Mars, you'd also have to restart its sort of volcanic systems and tectonic systems and so on. So I think personally, I'm very, very skeptical that even in the most optimistic projections would lead to anything particularly useful. So I think on Mars, you're limited to creating enclosed habitats. You could, people talk about tenting over some of the chasms and canyons on Mars, and that's perhaps not a bad idea, to essentially put a lid on some of these natural formations and use those as habitats. But, my sort of real conclusion from thinking about this for the book is that actually planets other than the Earth are probably not the best place for our future in the solar system.
I mean, even just all the drugs, the meds that the astronauts take on the International Space Station, every one of those drugs has some side effects. So then you take something for the side effects and you just get this cascading effect. And then if you multiply that over years or decades, we just have no idea what the consequences would be. All right, what about the O'Neill Space Station idea, where you're on the inner surface of the rotating space station, and that creates artificial gravity, and that solves some of this problem, maybe.
Yeah, so there's the option other than planets is to build structures between the planets, orbiting the sun, independent artificial structures or structures built out of things like asteroids and so on, where you can actually do a much better job at creating the sorts of environments that work for humans and for other terrestrial life. So the O'Neill cylinders is this lovely idea. It came from Gerald O'Neill in the 1970s, or some of it came from his students, because he set them the problem of, how would you sustain humans in space on a grand scale? And so O'Neill cylinders are these artificial structures. They might be 20, 30 kilometers long, 10, 15 kilometers wide, and they are big rotating structures, spinning structures that produce what is in effect artificial gravity on their interior because of centrifugal forces. And so if you spin a structure up, and you're on the inside of it, walking around, friction keeps you moving with that inner surface. And if you spin that surface quickly enough, you can reproduce the effects of Earth normal gravitational acceleration. It's easier with bigger structures because it turns out that human physiology doesn't like being spun around in what's essentially a large clothes dryer. So if you spin at more than a few RPM, few revs per minute, your brain doesn't like it. It doesn't appreciate it, and so it's like the worst funfair ride imaginable because you're stuck in it. But if you build a big enough structure, you essentially you can trick your brain and your body into forgetting that the force you're feeling downwards is actually because you're spinning around in this large circle. And so an O'Neill cylinder is big enough that you could essentially put an atmosphere in there. You could have liquid water. You could build your forests and your rivers and your lakes and your squirrel habitats and so on, all on the interior of a structure that is then orientated to point towards the sun at all times. And so you are solar powered. You can have day and night because you can modify the pointing, or you can have shutters that close off sunlight, and you can place these structures wherever you want in the solar system. So you could put them in orbits that are commensurate with the Earth's orbit, or perhaps slightly more optimal orbits, maybe a little bit closer to the sun, so you get better solar power. Or maybe you put them in a place where you're less prone to being hit by solar storms. So maybe an orbit that's a polar orbit around the sun. So yeah, and O'Neill structures are just one example of the possibilities for artificial habitats where you can reproduce the kind of gravity that we know works for us. You can reproduce really all the things that we know work for us, rather than trying to adapt us to those environments. You adapt the environment to us.
Well, as you point out, and many others have as well, we've already solved all of these problems, and we're living it with the Earth spaceship. We're going through space.
Yeah, absolutely.
But evolution solved those problems for us. The problem with evolution is it takes differential reproductive success, which takes multi-generations, genetic change, populational genetic change over time. That would take a long time living on different, planets, moons, other solar systems, millions of years. We wouldn't be the same species. We would just be some other species. But that just sounds like pure science fiction at this point.
I mean, I think at this point it absolutely is pure science fiction. But at the same time, if you follow the logic through to ask, what happens if the current sort of surge in space launches and our interest in spreading further into the solar system, what if that carries on, and what if that continues to take place? And one outcome could be the dilution and dispersal of us and other organisms on the Earth across a volume of the universe vastly greater than what we've experienced so far in terms of the surface of the Earth, which it's big, but it's not that big, and vastly more resources out there in the rest of the solar system. And so I think, one of the things I do in the book is try to consider these sort of boundary conditions. What are the possible endpoints? I don't know exactly how you might get there. What would that look like, and what would that do to us? And one thing we know is that when a species is dispersed and diluted, whether it's stuff scattered on, the young volcanic mounds of the Galapagos Islands or elsewhere on the Earth, what happens is a single species inevitably becomes multiple species. It speciates. That just seems to be what happens because each group is exposed to different conditions and so on. So the really big picture, the sort of the grandiose picture here is that, the future of humans spread across the solar system, it's not going to be us. It's going to be other versions of us, other descendant species from humans. And I actually personally find that quite a positive thing.
Oh, yeah. Oh, my God. It's so uplifting. Like, we could do this? So here's the question. So let's apply the Copernican principle to ourselves. We're not special. Somebody else surely has done this. So, where I'm going with this, the Fermi paradox, or we wouldn't be first. Somebody must have figured all this out. A million years ago. They could have migrated all over the Milky Way. Where are they? What is your answer to that?
Well, I have spent, in my other sort of research areas, I've spent time thinking about exactly that question. And I think, part of my answer is that we do tend to make the assumption that we should have seen something by now. Mm-hmm. And that's, I feel, a little bit arrogant on our part. And I'm as guilty of it as anyone. Mm-hmm. When you actually look at the extent to which we've deployed our technology to look out into the universe, whether it's listening for radio signals, whether it's using our telescopes to examine exoplanets, planets around other stars and looking for evidence of life there, we have really only just scraped the surface. So I think part of the answer is I'm not sure we have looked hard enough yet to actually really have a Fermi paradox. I mean, the original Fermi paradox was more about things coming here, right? Why hasn't another species sort of swept across the solar system? And to that, I would say, well, maybe it has. It's just, why would it happen in the last 200,000 years or even the last
Right.
2 million years? There's absolutely no reason for that. In fact, a few years ago, I did some work with some colleagues on precisely that question, where we tried to model, imagine the galaxy is full of spacefaring civilizations, and they perform interstellar travel all the time. But, the galaxy is a complicated place. It's not homogeneous. They may start out from one star and jump between stars and so on. And it turns out that when you do these simulations, it's not unreasonable to imagine that, there are these waves of explorers crossing the galaxy all the time. But the period in between when those waves pass through a particular system can be long. It could be 10 million years. It could be 100 million years. So it's not implausible that 10 million years ago something swept through our solar system, took a look, did whatever, maybe even had a civilization. It would all be invisible by now.
You mean erased because of the rock cycle, and it'd just be nothing left. Even the pyramids,
Exactly.
I've read, would be gone in a million years. There'd be nothing there but just sand.
No, and I think we have this conception because we see fossils. We think, oh well, the past is preserved, and of course, individual fossils, are incredibly rare. We see, one fossil out of perhaps 10 billion Tyrannosaurus rex that once lived on the Earth over a period of tens of millions of years. We are seeing incredibly rare remnants, and when you examine, for example, if our civilization just stopped right now, how long would it take for all signs of it to disappear? Not that long, a few million years, and all that's left is a few strange radioactive isotopes and possibly a few peculiar plastic molecules embedded somewhere. The rest is gone. So this is not to say that this happened, right?
Yes,
but
of course,
I think
right,
it's part of. So part of my response to the Fermi question is that I'm not sure we've looked long or hard enough yet to even begin to be worried that nobody's out there.
I mean, even the ancient alien people, their time frame is nothing compared to cosmic or geological time. It's just
Right.
1,000 years ago or 200 years ago. It's nothing. All this could have happened 10 million years ago. It'd all be gone. All right. I know you got to wrap things up here. Just a couple last questions. Three-Eye Atlas and Oumuamua and Avi Loeb's idea of searching, not just him, but others, but especially him on the, technosignatures, the search for Dyson spheres or O'Neill structures out in space or passing through our solar systems. Your thoughts?
So, looking for Dyson spheres, technosignatures, structures out there, I think that's valid. And we have some ideas how to do that, and some people have been trying to do that in a systematic and reasonable way. The issue of interstellar objects coming through the solar system and wondering whether they're artificial in nature, I think is an extremely tricky business. I think there's, as far as I can see, there's zero evidence that any of these objects are anything but natural phenomena, and they're beautiful, wonderful, interesting natural phenomena. Why is it happening now? Well, because we didn't have the monitoring techniques and the systematic surveys that we used to that we need to see these things coming through the solar system. So it's not so surprising we're suddenly seeing these things. I think it's, on the one hand, it's fine to raise the possibility, what if one of these things is an alien spacecraft? What if it is the remnants of, an interstellar transport that happens to be coming through the solar system? Yeah, fine. That's okay. But I think what's been unfortunate about the discussion around this is the sort of a willingness to ignore the scientific method, while at the same time suggesting that others are not applying the scientific method, right? By suggesting that we're not being imaginative, we're not allowing, we're not looking for the extraordinary, and so if we're not looking for the extraordinary, we'll never find it. I think that's grossly unfair on the part of certain people out there, and it's unfortunate because it undermines the whole nature of science and the fact that you have people who are expert in things. So every expert on asteroids and comets and interstellar objects will tell you what we're seeing are these beautiful natural phenomena, right? They're frozen nitrogen, or they're, other materials that have been in transit between the stars for millions, potentially billions of years. It's amazing, right? What an opportunity to learn something about the universe. So I find it very discomforting when people point at those experts and say, well, they don't really know what they're talking about. They're not being imaginative. It could be an alien spacecraft. It's like, come on, let's not go.
Yes. Well, there's so much we don't know, and this idea that, like the 3I Atlas is not acting like a typical comet, although that may have changed in the last few days. Maybe we just don't know that much about the billions of objects that are out there, and this is just one of those, and they're, with an N of 3, how can you draw any conclusions?
Yeah, absolutely. I agree. And also I think, the other piece of the notion that suddenly these things are artificial, alien entities or whatever, just as I happen to get interested in that, just as we as a species, for the last 100 years have had this interest in UFOs and so on. It's like, no. That's just no.
No, I follow this. I'm on Avi's Galileo project. I'm sort of the token skeptic there, and one of my wheelhouse topics is UFOs forever. So we've been hearing about this. This subject. Disclosure is coming anytime. So there's a part of that, like, this is it. It's finally here. Okay. But this also operates in what we call the low information zone. Things that are kind of blurry, grainy, you can't quite make it out. That's where, the imagination fills in. Okay, that's all fine. But why not just say, we don't know what it is. Here's like half a dozen things. But if one of the half dozen explanations is aliens, that's where the film crew goes. That's where Avi says, he's a film crew in his office every day, right? If he was saying, I think I found this new comet, they wouldn't be there with the film crew. It's like, well, whatever, another comet. Right. So there is something about extraterrestrials. What is your thought on that? Sagan used to say it's almost like a religious impulse, like the gods are out there. They know we're here.
Yeah, and I can sympathize, right? Wouldn't it be wonderful, right? Wouldn't it be extraordinary if there were, thinking alien beings or machines floating around our solar system or in our atmosphere? Yeah, it would be extraordinary. The one positive thing I will say that has come out of some of the attention to these things like the interstellar objects and UFOs and so on is there has been a bit more movement towards, let's get more data and let's do it in a more systematic way. You mentioned the Project Galileo, and that is an example of that, and I feel that's a positive development, right? People may get rather disappointed, but at least we'll have data, and we may find other things that are interesting, and they, even if they're not, aliens, we may find something interesting in that data that we hadn't understood before, and that's always a good thing.
Yeah. That's a good place to end it, Caleb. Thank you so much. Here it is again, The Giant Leap, Why Space is the Next Frontier in the Evolution of Life. Believe it or not, in an hour and a half, we barely touched all the super interesting details in here. I mean, it's just so amazing, all the different planets and all the stuff about spaceships, and wow. Okay. Anyway, well done. Thank you.
Thank you very much.